Okay, guys, so welcome to the chapter 11 slides, which is the first of the two sections on your favorite subject ever, which is statistics. Before I go through the slide material, I'll just make a few major points on this. I've gone a little bit away from the book here. So the book tends to do a lot of kind of quite advanced techniques, but in not much detail. So I've kind of cut down the number of techniques we covered, but tried to give them a little bit more detail. And I've also, because I've taught business stats too with the textbook that you use, I've tried to link it a little bit more to the material that you guys have actually used in business stats too. Now, when it comes to the actual revision for this section, this third, my revision guide will be a bit more detailed than normal because we've gone a little bit away from the textbook. I will be really detailed, and also I'll give you, which I didn't do before, I'll give you some actual example multiple choice questions on the sort of things I'm looking for. But, just to prepare, if you haven't burnt your notes already, do read through your business stats 2 notes. I can't cover everything here. This is just like 1 week, and we're covering the techniques, which is like 2/3 of the 8-9 weeks of business stats 2. So we're going to go through kind of lots of different statistical tests, and for each one, I'm going to kind of show you how you do the hypothesis. I'm going to show you how you implement those in SPSS, and then we're going to just talk a little bit about how to interpret the results in SPSS. So I'm going to try and keep it as practical as possible. So you won't actually need to know the hand calculations, calculating the T scores or the F scores, anything like that. We just don't have time to do that, and that's not really the focus of the course. Okay, so we finish off where we basically finished last week, in that we've got our data, we've prepared it, we've tested it to make sure there's not too much missing data, that people have filled things in correctly. We've checked for our response and non-response bias. We've maybe combined data from different databases, and we've tried to put it in a consistent format. And we're all ready to do some statistics. So with statistics, the whole idea of statistics is we're trying to make hypotheses. We've got some kind of state of being that we assume, and we're trying to prove against that. Now let's just try and not make this, let's try and make this a little bit more grounded. So we all know the NFL, and every time you score a touchdown in the NFL, then it's reviewed. And what we're doing is we're looking for evidence that it's not a touchdown. So we're trying to prove something different for the current state of being. So let's just do H0. And again, I apologize for my writing on this. I'm using kind of a really rickety old tablet. I'm going to try and upgrade this. So H0 is the touchdown is correct. That is my null hypothesis. And what we're trying to prove is we're trying to prove evidence for an alternative hypothesis. So the referees up in the booth who are actually reviewing this is the touchdown is not correct. And that is HA, which is the alternative hypothesis. Now, doing something like this is actually very difficult. We're building up evidence. It's not something we can easily put in a statistical model. So let's just give you the sort of example we would do some simple statistics on. So we have H0. And this is an example I'm going to give you in the moment. It's kind of, I guess it's pretty relevant at the moment, is a hospital is trying to look at its systems, and it's trying to make sure that the average patient stay is less than 5 days. So it's implemented a set of new systems, maybe like improve care or trying to get people out of the hospital quicker. And it's looking to see whether it's like meeting this standard of people, on average, people being out of the hospital in no more than 5 days. So we're going to say that the mean stay in hospital, my null hypothesis, is 5 days. And HA is my alternative hypothesis. It can be a big A or a little a, doesn't really matter. Apologize if I'm inconsistent. And the mean stay is greater than 5 days. Again, my writing is not the best on the board, and it's even worse on a pen. So that's just what a hypothesis is. A few more concepts, and I'll kind of link this back to business stats too. So, whoops. So the test statistic, this is basically, when we do statistics, we're taking samples and we're trying to, as we've talked about earlier in the class, and we're trying to use them to show, for population parameters. So for example, if you had, remember we had X bar, this was the sample mean, and this is, we try and do this for mu, which is the population mean. And essentially what a test statistic usually does is it's usually just seeing how close, in our simple examples, how close the sample mean is to the population mean. So our test statistics are things like you covered in business stats, and I'll give you an example in a minute. Things like the T, the Z, the F, and the chi-squared statistic. You remember all of these? Bringing back some happy memories? Okay, so a few more concepts. So a type 1 error, this is when we reject the null hypothesis, but the null hypothesis, in fact, turns out to be true. So let's just think about this in terms of our hospital example. So we conclude that the length of stay is greater than 5, but in fact it is 5. So we've made an erroneous conclusion. I'll talk about the rejection region in a minute. I want to draw you some graphs for that. But the type 2 error is kind of almost the converse of that. So here, the length of stay, we conclude we don't reject the null hypothesis. We don't have enough evidence. So we conclude length of stay. Sorry, I've lost my pen. Is 5, but in fact it's greater than 5. And you can see that these guys are kind of opposite. And in fact, on the next slide, this is kind of summarized nicely. So we have the two correct decisions. So in this case, the mean state is 5, and we assume that it's 5. Here, the mean stay is greater than 5, and we reject the null hypothesis, and we say, yes, it's greater than 5. And then these are the two errors we just talked about. So it's true, but we reject it, so it's 5, but we say it's greater than 5. And then the converse. It's greater than 5, but we say it's 5. So these things together, they give us a nice little symmetry. Okay. So we have 1 and 2 tail tests. I'm going to show you the kind of the distributions in a minute, so we won't do that. But let's just have a look at this. So this is this is my kind of example, my mean length of stay. Now imagine that we're looking in both directions. We're actually wondering, is it greater than 5? Is it less than 5? We may be doing much better than our standard. We may be doing much worse than our standard. So we want to check in both directions. So we're actually checking, is it greater than 5 and is it less than 5? We're checking both at once. So we're trying to basically prove it's different from 5. Here, a one-tailed test, we're just trying to show, yes, we're doing better than our standard. Or we could alternatively just do yes, we're doing much worse than our standard. So generally, when we use things practically, most people, I know in business stats, when I taught business stats with the book, we treat these equally, but 9 times out of 10, you're going to do a two-tailed test. Because it's a philosophical difference, but generally you want to look in both directions in case you have an unexpected result. We may think we're actually doing really well, but in fact we may be doing much worse. So this isn't there's lots of you can read, there's lots of papers on which one of these is the best and lots of philosophy, but we're a practical marketing research class, not a statistical theory class. So just be aware of the differences, but in practice, 9 times out of 10, we're going to be using a two-tailed test. We're just going to be, if we're looking one way, why don't we look in the other direction? Okay, so this is actually the data. I've got this in Excel. We're going to put it in SPSS in a minute. This is the actual data set for the length of stay. So this is we've actually sampled a load of patients maybe coming into our hospital system. And again, we're assuming a sample here. I guess a very good hospital system would actually be able to work out the length of stay by checking every single patient. But never mind. We will just assume we've got a large number of patients, and then we interview a certain number and we find out how long they stayed, and we've got this sample of consumers. We kind of calculate the mean stay, which is less than 5, but we don't know whether this is not significant or not. And also we calculate the standard deviation. So we're going to talk about that in a minute. And this is our first statistical test, which I'm going to kind of draw. Sorry, just give me a second. And I'll just pause Camtasia and just get... Okay, so let's go back to our hospital example. So let's just assume that we have our null hypothesis here. And let's just imagine for the moment we're doing a one-tailed. We're trying to show that this value is in fact greater than 5. Now, what we do when we hypothesis test, as you probably recall from business stats too, is we assume that the null hypothesis is true. Now, just a few points, we assume a normal distribution. Or, in fact, if we're doing for a z-test, or we could actually assume a t-distribution for a t-test. Now, just remember, in business stats, you would generally use that if n is greater or equal to 30, and you'd use the t if n was less than 30. But in fact, and your data were normal. But in fact, you can generally use the t in this instance as well. So you can use the t here, And this is because as your n gets bigger, your t distribution almost becomes normal, so can be used in this instance. And I'm going to talk about this because SPSS doesn't implement the z-test. SPSS only implements the t-test. So for the moment, actually, we're just going to assume a t distribution. Now, so let's just start here. Let's just imagine we have this distribution. And this is a beautifully drawn t distribution here. And we're going to have, in the middle, mu equals 5. Any hypothesis testing, this is basically the distribution of H0. We're assuming the mu equals 5, and then we're trying to see how far away we are from the mu equals 5. Now, generally, we can assume these distributions using something called the central limit theorem. So if n is big enough, this thing called the central limit theorem, which we're not going to, if this was a stats class, we'd talk more about it, kicks in and we can use these distributions. Now, this has a mean of 5, and it also has a standard error or standard distribution of s over root n. Now, again, we're not going to do the math, but think about common sense. If I was to take, go back to the example I gave in class, if I was to take a group of maybe 2 or 3 of you and randomly select you and ask how many calories you have a day, it's quite likely that I would get maybe 2 or 3 football linemen who are consuming 10,000 calories a day. I could grab 2 or 3 people on a diet. I'm still going to have a big standard deviation. However, if I take 1,000 students, it's going to be almost close to the population. If the average calorie of Mississippi State students is 2,500, I might get 2,450. So the bigger the n, the closer we are to the population. So the bigger the n, the more accurate we are. Now, what we usually do in stats is we will try and turn this into a distribution of mean 0 and standard error of 1. So let's just draw a line to a new distribution. And here we have maybe an x bar. So this is the mean we find in our sample. And what we would do is we would subtract the mean 0, which in this case is 5, and divide it by the standard error. And this means we end up with a distribution where we have a 0 in the middle and a standard error of 1. Now, the only reason we do this is because when people started doing statistics, they didn't have Microsoft Excel. They didn't have computers. So we wanted to work out, how far along and probabilities on this curve. But we did it using these standard tables that you get at the back of statistical test books. And obviously, you can't provide a single table for every different mean and standard deviation. So we just convert everything to a mean of 0 and a standard error, standard deviation of 1. And then we just have one t table, one z table at the back. T is a little bit more complicated because depending on your n, you have different degrees of freedom. Okay, so everybody got that. Let's clear the canvas. So now we have this standard kind of distribution with a mean of 0 and a standard error of 1. So here we have, this is the 0 in the middle. And then we're going to have some sort of t statistic. So imagine that my t was 5.5. Sorry, my t was 1. So we convert my sample mean and we get a t. 0, this is like the h0 value because we've subtracted the mean. Now I want to know, am I far enough away that this is significant? So let's just say we're doing a one-tail test. So we're going to do h0. And let's just do the example we did. We have mu equals 5 and HA mu is greater than 5. So what we want to do is we want to see, is this significantly large? And how do we do this? Then we have rejection regions. So we have a value called here, which is alpha, which in this case, it's usually going to be 0.01, 0.05, or 0.1. This is actually the type 1 error. And basically, with the type 1 error, what we're going to do is, this is like how strict our test is. The smaller the type 1 error, we've got to go much, much further in order to kind of reject the null hypothesis. So this is just an area in the curve. And the area, the rest of this is going to be 1 minus the type 1 error. And we would actually call this is our rejection value of t. And this is going to be t alpha, which is our type 1 error, and then the degrees of freedom, which is n minus 1. We're not going to worry too much about it for this class because it's not a stats class. So we generally reject the null hypothesis if t is greater than this t starred fella here. So imagine that we kind of start off, and this is mu is 5. And at 5, we have no evidence. Maybe we get to 5.1, 5.2, 5.3. And eventually, we kind of have enough evidence. So across here, we're building evidence. So then we reject the null hypothesis and say there's evidence for the alternative hypothesis. Now, what makes it a little bit different in SPSS, so let's draw a third one. So imagine we have our t value here. This is my t starred. And everything to the right of this, we're going to reject. So everything here, we're going to actually reject. And we have an actual t. So I'm going to have a t value here. And you can see we're not far enough along, and we're not going to reject. And imagine this guy is alpha equals 0.05 to the right. Another way of rejecting is we say, look at all this area to the right of my actual t value. This is called the p-value. So this is the probability more extreme than my actual t-value. And we can also say exactly the same. Again, as we go to the right, my p-value gets smaller and smaller. And when t hits t star, my p-value is 0.05. And if my p-value is less than 0.05, I'm in the rejection region. So we can also reject if my p-value is less than 0.05. Now this is a little bit, people always find this tricky. My t-value is getting bigger, but my p-value is getting smaller. And once my p-value hits that 0.05, then we go through to the rejection region. So say, let's use the third color. If I have a t here, and imagine the area to the right is 0.005, then I'm going to reject. I'm not going to reject the one in blue, but I'm going to reject the one in green. Okay, So now let's go back to red, and let's do the other direction. And again, let's just go with my length of stay example. So we'll stick with mu is mu naught equals 5. So now we're checking if the length of stay is less than 5. Here we have my alpha, my type 1 error. So again, we start in the center where our mu's get less than 5, and eventually our t-values get less and less and less until we hit the critical region, and we're going to reject. And so this is going to be my t star. So here we're going to reject H0 if my t star, and in this case we're looking to the left, so I'd reject if my t is less than my t star, which is going to be t minus alpha with, in this case, my degrees of freedom. But again, don't worry about that. We're just worrying about directions at the moment. So imagine again, we get a t value here, which isn't, it's not kind of extreme enough to reject. We have the p value here, which is just the area to the left. And again, as this gets further and further to the left, my p-value gets smaller and smaller until it hits alpha. So again, we're going to reject H0 if p is less than alpha. Now you notice why this is actually nice. It's because we're testing the same thing every time. When you're doing this in business stats, you have to think, am I positive, am I negative, am I looking for big t values, small p-values. Here we're just looking for very small p-values. So again, in this green, maybe we have a p of 0.05, which is less than 0.5, so we're going to reject H0. So this is the key to doing well in this section. We always reject the null hypothesis. You need to understand how the hypotheses work, and you need to understand that we reject if p is less than or equal to alpha. Okay, so let's now do our third one. Whoops. And this time we're going to do a two-tailed test. Yeah, I might as well make this one big. So here we've got our mu equals 5. Now, interestingly, we have basically our rejection. This is going to, probability is split into 2. So we have alpha over 2 here. And again, what we do is we have kind of we have a t, which is going to be t alpha over 2 with n minus 1 degrees of freedom. And we're also going to have a minus alpha over 2 with n minus 1 degrees of freedom. And we're going to reject. Now this time what we're going to say is if the absolute value of t is greater than t alpha over 2. And this is just because it's symmetry. If this is like, say for example, this was 1.71 and minus 1.71, if I have minus 2, then it's going to be greater than 1.71. So just by slipping the absolute, we can put these two into the same equation. Okay. Now let's have imagine we're positive and imagine we get a t here. My p-value is here, but we're actually covering both sides. So my p-value is here as well. So when we're doing a two-tailed test and we get a p-value, we need actually to have 2 times this area. Now with SPSS, this will all be done automatically. But just one thing is, I'll just write this down. SPSS gives two-tailed p-values. So what we have to ensure, if we're doing a one-tailed test with SPSS, we need to divide the p-value by 2. Because here we have to multiply it by 2. So again, we're going to reject H0. And this is why this is nice, because we're doing basically the same test every time. We're rejecting if P is less than or equal to alpha. Okay. So again, let's just keep consistent. Imagine we have a rejection here. And we've got a really big t value. We still have it on either side, but in fact it's less than alpha. So again, we're going to, with this green one, we're going to say that the p is less than alpha, so we reject H0. Okay, so I'm actually going to stop this video now. I want to kind of break this up as it's a big topic. But just a few things. Go back to your original business stats notes. Once we actually begin to do this in SPSS, it actually will seem a lot simpler because you'll be pretty much doing the same thing. You'll be rejecting if your P is less than alpha on each of these tests.